engineers across the globe have been racing to design smaller, cheaper, and more efficient rechargeable batteries to meet the power storage needs of everything from handheld gadgets to electric cars. In a paper published in the journal Nature Nanotechnology, researchers at Stanford University report that they have taken a big step toward accomplishing what battery designers have been trying to do for decades. That is, design a pure lithium anode. All batteries have three basic components: an electrolyte to provide electrons, an anode to discharge those electrons, and a cathode to receive them. Today we say we have lithium batteries, but that is only partly true. What we have are lithium ion batteries. The lithium is in the electrolyte but not in the anode. An anode of pure lithium would be a huge boost to battery efficiency. According to the leader of this research team, lithium has the greatest potential comparing to all other materials that one might use in an anode. Some call it as the Holy Grail. It is very lightweight and it has the highest energy density. You get more power per volume and weight, leading to lighter, smaller batteries with more power. But engineers have long tried and failed to reach this Holy Grail. Lithium has major challenges that have made its use in anode difficult. Many engineers had given up the research, but the Stanford researchers found a way to protect the lithium from the problems that have plagued it for so long. According to the researchers, you might be able to have a cell phone with a double or triple the battery life, or an electric car with a range of 300 miles that cost only $25,000. In the paper, the authors explain how they are overcoming the problems posed by lithium. Most lithium-ion batteries, like those you might find in your smartphone or hybrid car, work similarly. The key components include an anode, the cathode, and an electrolyte. During charging, the positively charged lithium ions in the electrolyte are attracted to the negatively charged anode, and the lithium accumulates on the anode. Today, the anode in a lithium-ion battery is actually made of graphite or silicon. Engineers would like to use lithium for the anode, but so far they have been unable to do so. That's because the lithium ions expand as they gather on the anode during charging. All anode materials, including graphite and silicon, expand somewhat during charging, but not like lithium. Researchers say that lithium's expansion during charging is virtually infinite relative to other materials. Its expansion is also uneven, causing pits and cracks to form in the outer surface, like paint on the exterior of a balloon that is being inflated. Preventing this buildup is the first challenge of using lithium for the battery's anode. The second engineering challenge is that a lithium anode is highly chemically reactive with the electrolyte. An additional problem is that the anode and electrolyte produce heat when they come into contact. Lithium batteries can overheat to the point of fire or even explosion. The recent battery fires in Tesla cars and the Boeing's Dreamliner are examples of the challenges of lithium-ion batteries. To solve these problems, the Stanford researchers built a protective layer of interconnected carbon domes on top of their lithium anode. This layer is what the team has called nanospheres. The Stanford team's nanosphere layer resembles a honeycomb. It creates a flexible, uniform, and non-reactive film that protects the unstable lithium from the drawbacks that have made it such a challenge. The carbon nanosphere wall is just 20 nanometers thick. It would take some 5000 layers stacked on atop another to equal the width of single human hair. The Standford nanosphere layer is made of amorphous carbon, which is chemically stable yet strong and flexible so as to move freely up and down with the lithium as it expands and contracts during battery's normal charge-discharge cycle. In technical terms, the nanospheres improve the coulombic efficiency of the battery, a ratio of amount of lithium that can be extracted from the anode when the battery is in use compared to the amount put in during charging. Generally, to be commercially viable, a battery must have a coulombic efficiency of 99.9% or more, ideally over as many cycles as possible. Previous anodes of unprotected lithium metal achieved approximately 96% efficiency, which dropped to less than 50% in just 100 cycles. The Stanford team's new lithium metal anode achieves 99% efficiency even at 150 cycles.